So it's a pleasure to introduce Chris Osterwood. He is Chief Technical Officer at Carnegie Robotics. He's been there for 6 years and has led the development of many of Carnegie Robotics component products in custom robotic systems, including their trade product, Multisense. A number of things he's done. He's done multi-purpose built manipulators, off-road, unmanned ground vehicles, indoor autonomous robots. So he's done quite a bit. So today he is in charge of leading industry partnerships and developing customized versions of Multisense. He has a mechanical engineering degree with research honors from Surprise, Carnegie Mellon University. And so we're very excited to have him talk today. So please welcome Chris Osterwood.
So much. Again, I'm Chris Osterwood. I'm the CTO at Carnegie Robotics, and I'm going to talk about how we choose 3D sensors, how we evaluate them, and hopefully illuminate some of the edge cases and trade-offs between some popular 3D sensor modalities. Carnegie Robotics does two things. We build robotic components as well as custom systems, headquartered in Pittsburgh, and do this across a wide variety of industries. We're in the agriculture, military markets, industrial floor cleaning, and a whole host of other things. We're about 70 people, 7 years old, and we build our own stereo cameras and also integrate lots of other kinds of 3D sensors into the systems that we build, which is where a lot of the data and the results that are in this talk have come from through those integration efforts. So we're going to first start with criteria and definitions, give you some fundamentals on the verbiage that we use to talk about these sensors. And then we're going to do an overview of 3 different kinds of 3D sensor modalities, LiDAR systems, time-of-flight cameras, as well as active and passive stereo. And that'll include a very brief summary of how they work, what are their general advantages and disadvantages, as well as some sample data from a single environment to sort of show you qualitatively how these sensors behave and how they work. Then we'll go into a little bit more detail on 3D sensor testing and some edge cases, and this is a little bit more quantitative with some results from laboratory testing that we've done, and finishing up with some final thoughts. I'm going to note that we're not covering many other kinds of 3D sensor technologies like computed tomography, structured light, and laser triangulation. Those are appropriate for many kinds of systems, but not for the mobile outdoor robots that we build, so we don't have the same kind of test data and insights into those modalities. So we're focusing today on LiDAR, time-of-flight cameras, and stereo. So when we think about 3D sensors, we classify criteria into 2 different groups, performance criteria and non-performance criteria. And performance criteria in our language means anything that affects the quality of the data that comes out of the sensor, and everything else is non-performance criteria. Field of view should be fairly well understood. It's the angular area that's perceivable by the sensor. And that's the way we always think about this in terms of angular field of view for all the sensors that we use. And within that angular field of view, you have some density of the returns, which is the angular step size between all the different sampling points. And that can be different horizontally and vertically depending on the sensor modality. This is especially true in laser systems, where you'll have much higher angular field or angular density between adjacent points of the laser, and then less density between adjacent laser scan lines or between adjacent emitter detector pairs. And when you combine those two together, density and field of view, you have resolution. And here I mean field of view resolution, not depth resolution, which is very different. And the next very important performance criteria, and that we define as the distance between measured range and actual range. And that's critical to 3D sensors. That's why we use 3D sensors, is to compute depth, so depth accuracy, and in parallel depth resolution are very, very important for these systems. And it's important to understand that there are differences between the two, that sensors have some general accuracy, then they generally have a higher resolution of data that they return at. And there are advantages to having higher resolution even without absolute global accuracy. It does sometimes let you find smaller features in an environment, even if those features are slightly off in terms of distance globally from your sensor. And there's also minimum and maximum range for most of these systems. Depending on the use case, one or both of these criteria may matter. And they do vary rapidly by the kind of sensor modality, as well as the actual implementation that whichever vendor you're buying your sensor from. And for some of these sensors, that does vary by the environment that the sensor is operating in. They may be limited outdoors. They may be limited with dark materials or very reflective materials. So it's something to pay close attention to. And finally, rate, which is frame rate for cameras or point rate for laser systems. That's just how quickly you're getting data from the sensor. On the non-performance side, there's the classical size, weight, power, cost, SWaP-C, which matters a lot when you're building an unmanned ground robot. Things that are bigger and heavier draw more power, have compounding effects on the design of your robotic system. If you can minimize power draw on your sensors or weight, it results in a smaller, lighter, more mobile robot that will run for more time. And for both indoor and outdoor systems, sealing and shock and vibration ratings matter greatly for these sorts of systems that we build. Even indoor robots go over sharp thresholds, have transportation vibration and shock, and do see cleaning operations and things like that. So sealing is a big factor of how we evaluate sensors. Of course, you have a communication interface both physically and in software, and depending on the rest of your system, you're going to prefer one of these many different kinds of physical interfaces. We generally prefer Ethernet for the sensors that we integrate and the systems that we build. We find it to be a very robust protocol. Electrically, it has high enough data rate for the systems that we build, but there's a wide variety of different communication protocols. And then in terms of software interfaces, it's something to pay attention to. We run into all sorts of unexpected snafus in integrating sensors onto systems where we have a binary driver and it expects there to be a single one of these sensors on a system, and we want to use 4. So trying to have one binary driver talk to 4 sensors when it wasn't designed to do that becomes quite problematic. And when you have multiple sensors or a sensor feeding a more distributed system, synchronization of timing between the sensor and the rest of the system becomes very critical. And that can be done through hardware triggers, a pulse per second signal, some kind of master clock through your robot or your whole system, or with software like broadcast triggers or a network time sync. So depending on the platform that you're building on, the kind of application that you're using, the 3D data for from a end-use data perspective, the weighting of all these different criteria change. And this is a very, very short snapshot of a couple of different platforms and a couple of different applications. There's obviously a huge host of other uses for 3D data. And for every single environment and end use, you will care about these criteria differently. And it's very important for you to consider what is important and what is not important to inform the decisions you make about the 3D sensors that you select. Just highlighting a few things on this chart. Here, orange is a higher rating and yellow is a lower rating. And you see that for indoor ground robots, the vertical field of view for safety matters a lot, which is different than any of these other applications. If you have a robot driving around inside, you are looking for drop-offs, you're looking for a fire extinguisher on the wall, and having large vertical field of view on your safety system helps a lot in detecting those obstacles. Similarly, you care about having a very short minimum range. You don't want some obstacle to get between that minimum range and your robot and then become invisible to the safety system. And then you see for mapping that things like horizontal field of view and maximum range and system accuracy matter a lot more than for safety applications. Okay, so now we'll talk a little bit more in detail about these 3 different sensor modalities, starting first with 3D lasers. And 3D laser systems are generally built from one or more single-point laser systems. There's a transmitter that emits a modulated laser beam. It hits some target. A reflection is returned back towards the sensor and in many other directions. And then you do a phase-based measurement between that transmission and the return, and you figure out how far away the object is. There's also time of flight, like pulsed systems, but generally these lasers are more modulated phase measurement based. And you can have that one beam steered mechanically in 2 degrees of freedom, or have multiple laser emission and detector pairs steered in 1 or 2 degrees of freedom, and you can steer them in all sorts of different means and mechanisms. And there are lots of people working on solid-state LiDARs, but those are not generally available in the marketplace yet. It will be exciting days when that is possible. But for now, 3D lasers either use a whole host of single points or some kind of mechanism to sweep a smaller number of single-point sensors. The advantage of these sorts of systems is that they can have very, very long range. They are generally very accurate, 1 sigma errors of a few centimeters generally. And they have a wide horizontal field of view due to the kind of mechanisms that are generally used to sweep them through the space. And they can potentially have vertical field of view ranges that are very nice and large, but that really depends on the laser arrangement and the mechanism. Things like the Velodyne have a relatively narrow vertical field of view and 360-degree horizontal field of view. Like our SL, which is on the bottom there, has about a 270-degree spherical field of view. The downside for all these systems primarily is cost. The trends are definitely encouraging, but there today is no very inexpensive laser-based systems available. And there's also scan time. Because you're talking about these discrete sensors that are being swept through an environment, you don't have instantaneous horizontal and vertical field of view. You have to wait for a scan to accumulate, and then if your system is moving through the space during that accumulation, you have to compensate for the platform or the mechanism movement during that scan. As I mentioned previously, there are asymmetric densities and generally limited density in comparison to some of the other systems that I'll talk about next. And of course, because you're emitting something into the environment, you're putting data out into the world, these systems are affected by obscurity in the environment. If there's dust or snow or rain or things like that, they are more affected than passive systems. Time-of-flight cameras are like LiDAR from a measurement perspective in that they do phase-based measurement, but instead of a single point that does measurement and detection, they have a more broad field of view emitter and then an array of detectors in a grid, sort of like an image sensor, a little bit different from the technology perspective. This results in instantaneous horizontal and vertical field of view, which is fantastic for a lot of applications, but the detectors are less sensitive, and that results in limited range or more optical transmission power that's required. And just like laser systems that are doing phase-based measurement, and there's a sort of a tricky thing there in these modulated waves. They overlap, and you have ambiguous returns that are correlated to the emission modulation frequency. A quick example here, if you have a 30 megahertz wavelength, that's 10 meters wave to wave. Due to the way the phase-based measurement works, you can't actually measure anything without ambiguity beyond 5 meters. Something that's 1 meter away and 6 meters away look identical. So before you run at 30 megahertz, you have to run at like 14 megahertz, which has a longer ambiguity detection region to figure out which of those two bins your object is actually in. You flip to the higher modulation frequency and you get a better range return on that target. So because of this cycling through different modulation frequencies and the difficulty of extracting the phase measurement from the signal, you have fairly long integration times, which is a result of this signal-to-noise extraction problem. And that can cause motion blur if the platform or if objects are moving in the scene. But there are definitely advantages. You have instantaneous dense horizontal and vertical field of view. You have linear error with respect to distance, which is a great advantage in comparison to stereo, which I'll talk about next. And also differently from stereo, you have a single shadow behind positive obstacles. Stereo, you actually have 2 projected shadows behind positive obstacles, which can cause issues in some environments. They are solid state, planar windows generally. That makes them easier to build, mechanically robust, more survivable in sealing and high vibration and shock environments than laser systems generally. But they are limited in terms of field of view. We haven't found any of these systems that are available beyond about a 60-degree horizontal field of view, and that limits their use in mobile applications. And they also are really susceptible to multi-echo returns distorting the data, and I have some examples of that in the coming slides. In comparison to stereo systems, they're also low resolution, and you'll see that in the coming slides as well. So stereo cameras work in a very different way. They work just like your eyes do, looking for texture in the scene, and then looking for shifts between left and right cameras, and that shift is inversely proportional to the distance that the target is away from you. So things at infinity don't move at all. When you observe them with your left eye and your right eye, things that are very close move much more greatly within my field of view. So if you have a very accurate understanding of camera baseline and lens distortion parameters, you can use that shift to figure out how far away that little piece of texture is. And this is called a matching or correspondence problem, and that's critical to data accuracy and density. There's lots of different ways that this matching process is done. There's been discussed in a number of talks here about new approaches of using neural networks to do this correspondence problem, which are really interesting, but not yet at a sort of power and reliability perspective to be in fielded systems. And I guess the other thing I'll note is that there's always a disparity search range that cameras look through before they sort of give up and move on to the next pixel. And that search range lets you see things that are closer to the system, but generally as that search range increases, the field of the data rate or the frame rate of the camera drops because it's doing more and more computation to pull in that minimum range and look for close objects. So in comparison to these other systems, you can build these cameras with much higher resolution and density because they use normal imagers. There's really no limit in terms of the resolution that you can build a stereo camera with. As the resolution increases, the computational complexity of the search becomes more and more difficult, and the calibration process becomes more and more difficult, but there aren't sort of fundamental physical limitations to resolution and density. You do get instantaneous horizontal and vertical field of view, and you also have very flexible field of view and baseline options because of how these systems are built. You can build stereo cameras with 10 degree up to 130 degree horizontal fields of view and everything in between, and baselines of whatever distance you need for whatever depth accuracy you care about. You can also get, if you use color cameras, immediately correlated color data with 3D data, which is really useful. Instead of having an adjacent RGB camera next to your time-of-flight camera, you can get RGB and depth from the same data stream. But these systems are dependent on scene texture to actually give you any kind of data at all, and that means that you have to be in a texture-rich environment or use an active stereo system that's projecting texture into the scene and allowing that to augment the correspondence problem. And I mentioned before that double shadow behind positive obstacles. That's because to get a return, both cameras have to see whatever piece of scene they're looking for. And behind this podium, my two eyes see slightly different field of view obstructions. So it actually casts two shadows through the world, one from each of my two eyes. Same thing with stereo. And in comparison to all these other systems, the error model for stereo is very, very different. It's a triangulation-based system, so it's a nonlinear error. As range increases, error increases, and it's worse than linear error increase. This does present problems in software systems that assume a linear error model, and you have to do a lot of tricks to sort of compensate for the range inaccuracy on these systems. But it also, because it's how these systems work, there's no maximum range generally for a stereo camera, unlike a time-of-flight camera. So they are very useful in mapping and safety tasks. You just have to know that they are not going to judge the wall of this room on the other side of this hall from me, as well as the distance to the podium. There's this very different accuracy measure between near and far. Okay, so to show you one example of the difference between stereo and laser, this is data from the DARPA Robotics Challenge. This is data that the MIT entry team collected from the Multisense SL, which pairs these two modalities together. And they're first showing here footstep planning and stair climbing using stereo data, doing instantaneous frames. There's no aggregation or accumulation of data here. It's just instantaneous frame by frame, which lets them move very quickly and respond to dynamic obstacles in the environment. In comparison, rotating laser-based systems or 3D lasers, you do have to accumulate data over time. So here, every couple of seconds, you'll see the whole scene sort of snap and update, and a single scan line going through the scene, accumulating new data. So you can do the same thing with both of these. The way you do it is different. The kinds of obstacles you see are different. You also see here that the rotating laser has a much, much wider field of view. You're actually seeing the whole scene, the room, instead of just the area of interest. So on these next couple slides, I'm going to show data from all these different systems in the same scene that we mocked up at our office, which is in our high bay. We have a little cart here. A person walks towards the cart, which you see bends down, moves a chess piece on a chessboard, and then walks out. And we're going to look at this with laser, time-of-flight cameras, and stereo. You see here that we're accumulating 8 seconds of data, and then it'll flip in a second to 1 second of data persisted with a higher rotation rate. And again, you see the differences in horizontal and vertical resolution, sort of in plane and out of plane of the laser system. You also see on the edges of this cart that it sort of looks like it's been draped with a cloth. These are called mixed pixel returns, and they're actually caused by a partial return on the cart and a partial return on the floor, and the lasers can't resolve that, and they put a point in space right in the middle. And you also see that you can get fast update data, but it gets sparser and sparser the more quickly you want to see the world, and that results in sparser data, which makes it harder to identify objects and harder to see the person walking through this scene. This is the same scene viewed from the top using a low-cost time-of-flight camera. You see here instantaneous horizontal and vertical field of view. We're not accumulating any data, just immediately displaying it, and the colorization is by axis. So red is ground, and then up to blue, high up. There's a lot of interesting things here, like there's some returns in the middle of the air. You can't actually see the top of the cart handle, but you can see the shadow of the cart handle on the background. And about half the floor is missing, which I was very surprised to see because it's not that far away from the camera. You also see that the bottom of the cart there, or the bottom of the handle, is really distorted, and I have a better example of this sort of mixed pixel multi-echo returns causing distortion. Here we have changed to an intensity colorization on the scene, and you see this flashlight effect where the IR emitters provide great illumination on near-field returns, but that the background is very dark and in contrast to the near field. We have an example of this causing problems in terms of actually perceiving objects that are far away when you have objects that are close to the camera. Here we have an industrial time-of-flight camera that goes totally crazy when someone walks right in front of the camera. There's these huge geometric distortions, but you see also that there's higher resolution, higher frame rate from this camera. It definitely performs, is providing more data to the use than the low-cost time-of-flight camera. But you also see that there's a lot more mixed pixel returns in the middle of the air. And then as the person's walking back and forth in front of the background, it's actually causing distortion and bending to that rear wall, which I really can't explain. As you see, if they walk across, it's almost like a big zipper or something moving across that wall surface. And the wall's not moving, but near field is causing distortion to the far field. Additionally, from the side there, you may have seen briefly that there was big distortion and bowing in the floor caused by the multipath returns. This is the same scene with stereo. You see immediately that there's the correlated color and range data, a wider field of view to the scene, and unlike these other sensors, you now introduce the range accuracy problem that stereo has, where the rear surface of this scene has lower accuracy than the near. You also see that there's some data below the floor, the incorrect matches that are being caused by reflections in the floor. That's actually a light that's up above this scene that the stereo camera is seeing as a reflection on the epoxy surface of this floor and then putting below the floor surface. Right here on the zoomed in view, we're actually adjusting the threshold of the cost that the matches are returned at. So we start with very dense stereo data and then ask the camera to successively return less and less data by increasing the confidence that it needs to send us that data. So at the end here, you see that the checker of our engineer's shirt turns out great, but that a lot of the other scene drops away because of the higher match cost from these less texture-filled parts of the scene. So you have this dynamic capability in more data that is less accurate or less data that is very accurate from these sorts of systems. And here we're also showing stereo data, this time augmenting it with a IR-based pattern projector, and you'll see it flick on and off as the scene plays through. With it on, it fills in some of the holes in the floor, causes there to be more texture in the background, which increases the accuracy of the matches on that stack of panels in the back, which reduces the range noise. It also cleans up the front edge of the cart and things like that. And the stereo algorithm has no knowledge of the pattern being projected here. It doesn't know anything about this. It's just texture like anything else is texture, but it can use this artificially projected texture to increase the accuracy of the data. This works very well inside to help improve the accuracy of stereo-based systems, but outside, these systems are generally overwhelmed by natural light, and the pattern projectors don't really work. Luckily, outside, there's a lot more texture than there is in indoor environments, so texture projectors are not generally needed. And because stereo cameras just use image data, you can actually use any wavelength of image data that you want. On the top half of the screen here is optical stereo from a camera, and you see the density and the data rate of this camera. And then on the bottom, we're generating 3D data from thermal stereo. So this is 2 thermal cameras that have been calibrated in the same mechanism. And the ground doesn't have enough thermal texture or thermal gradient to actually give any kind of return. But you see that the person and the buildings and the cars have enough thermal texture to provide range data. And interestingly, the air around the power lines also has enough thermal texture to provide range information, which is why there's that big red swath through the sky. That's actually warm air around the power lines. So in terms of general sweet spots between all these different modalities, this is an analysis. There's lots of other ways that all this can be mixed and matched in terms of advantages and disadvantages between all these different modalities. But LiDAR we generally see as very useful for high-speed vehicles due to its range and its wide horizontal field of view. If you have systems that have high steering rates, that's very, very useful. Time-of-flight cameras are generally most useful indoors. Short-range object scanning. We have a slide coming up showing that there are difficulties in having near and far range returns with time-of-flight cameras, but they are very useful in short ranges for gesture recognition, and they're very low cost. Stereo cameras are generally most useful outdoors and in high obscurant environments where anytime that you're projecting information to the world, you have more and more issue trying to extract signal from that, from noise caused by obscurance. And then, of course, anything that requires a passive solution, military applications and things like that, stereo is a great fit. So now I'm going to get into a little bit more quantitative results on some of these systems and showing a few different comparisons and edge cases between them. First, this is time of flight and stereo outside our building. These views are basically top down on the scene that you see here, which is a little foot scrubber and concrete pad and gravel. And you immediately see the difference in fields of view, in density between these two different sensors. And you also see that the time of flight camera has this sort of draping mixed pixel return issue on the edges of objects, while the stereo system does not. You also see much more of the wall surface and into the roll-up door on the left-hand side of the scene with the wider field of view stereo. This is taking the same 2 sensors inside and looking at an indoor hallway in our building. So the scene image here is a little bit off from the isometric 3D views. That little first aid box is actually out of view vertically in these 3D point clouds. The 3D cameras were looking more at the ground and the bottom half of the wall where the fire extinguisher is protruding from the wall. And you see with the time of flight camera that you get great range returns on that wall. It's really, really dense and beautiful. The floor comes out great for about 1 meter, maybe 1.5 meters, and then disappears. And in comparison, the stereo sees the protruding fire extinguisher totally misses the rest of the wall. There isn't enough visual texture on drywall to get any kind of match, so it just looks like empty space. But it actually is able to see the far wall and the far door beyond the visible range of the time-of-flight camera. That's because the time-of-flight camera is getting so much IR energy from this near wall that it doesn't have enough IR energy from the far wall to extract signal from noise and find that phase-based offset on the far wall. Taking this time-of-flight camera downstairs to our entryway and where our elevator is, here we point it at a shiny floor and an aluminum beam that is next to the elevator, and you see this multipath return problem that time-of-flight cameras can have. Here there's actually 2 different distortions overlaid. You have sort of a groove cut into the floor that's a mirror of the column. And then you also see major distortion to the column shape caused by IR energy hitting the floor, reflecting off the floor, and then being returned back from the column direction. And the immediate returns from the column are getting distorted and elongated by the longer returns of this path through the floor up to the column and back up to the camera. And then when the system is trying to do that phase-based measurement, it looks like the column is farther away than it actually is because of this multipath data. You can use polarization filters to cut out the multipath returns, but you're losing a lot of energy from the scene that you're emitting, so it really severely impacts the maximum range that the sensor can be used if you have sort of a filter in front of this. In high obscurant, you can end up with situations like this. Here we put a 3D laser and a stereo camera in a tunnel, filled it with artificial smoke, and you see that the laser system sees the smoke. It's just getting infrared energy off the particulate in the air, and it isn't able to see through that to the actual scene. The stereo camera, has a reduction in contrast, which causes a reduction in accuracy, but just like your eyes can see through smoke into the world and make out objects, so can stereo cameras. There's a lot going on this slide, and I'll walk you through a few things just on the layout here before I talk about the results. And there's a couple of these that show differences between different kinds of sensors. So we have a material test target, 6x6 grid of different kinds of materials and surfaces that you find in indoor environments, arrayed in a grid. And then the left and right dot pattern boards on the center and the left of this image, are range results from the camera or the laser looking at this dot pattern board. So the top left of the range board is the top left block, and things like that. We've labeled some of these here, the black tile near the bottom. And then we're testing this system with ambient illumination as well as halogen-based illumination, which is much, much brighter and has a lot more IR energy. And you see that this 3D laser from vendor A has relatively similar performance between ambient illumination and high IR illumination. The one weird thing is that some of the white areas actually shift in front of the objects that are being measured instead of being behind the objects. So you see that 2.5 centimeter shift. This is the same kind of sensor from vendor B. You immediately see that there's about 50% more noise in all this data than from the previous slide. And then when the IR lights turn on, there's another 40% noise on top of all that data. So this is the same sensor. It's a 3D laser just like previously, just a different vendor, and their implementation is much more susceptible to IR noise in the environment, and it's corrupting a lot of the data. The top row here is the standard deviation of returns, those numbers along the top of the top row, and we've analyzed all this for every single row, but not displaying that here, just to give you some sense of scale on these measurements. We've included just the top row. You also see that the objects that these two different systems see change. So vendor A, on the second row on the right-hand side, there's a brass wall plate, like a light switch panel. It sees it just fine. Vendor's B laser totally fails, can't see that brass plate. It's defective. Moving on to a time-of-flight camera, here you see higher range on dark objects, less sort of more normal range on the rest of the objects. And then when the IR lights turn on, all of the noise increases by a factor of 2 to 5. And I mentioned previously that these are doing phase-based measurements, but they're using an array of sensors instead of a single sensor. So they have a more difficult challenge in extracting signal from noise, and that's what's causing this increased noise with the high IR energy in this scene. In comparison, stereo doesn't have that kind of ambient IR issue, but it does have variable accuracy with range. You see here as we pull back the 7 centimeter baseline stereo from 0.5 meter to 1.2 meters, that there's more range on lower texture targets. It becomes harder and harder for the stereo camera to resolve accurately. I'm sorry. But you're still getting range, it's just more and more inaccurate. This is another test we ran on some 3D lasers where we put them on a robot arm that we have, we scanned a flat wall, we pulled at a 5 centimeter increment and then plotted all that data on a single plot here, colorized by range accuracy. So this is between basically touching the board at 5 centimeters up to 1.5 meters. And this is 2 different lasers that are available from the same vendor. One is price X, one is about 3 times as expensive. And you see that there's a tremendous difference in density between these 2 systems. That is very observable from the data sheets and from this data that the more expensive system has much higher angular density than the low-cost system. But what you don't expect and what you can't tell from the data sheet is that the low-cost sensor also has range and bearing dependent error. So there's this spot in the middle of the data where all of the data is offset by about 1.5 centimeters or more. And it's not just range dependent, it's not just emission angle dependent, it's actually a combination of the 2, which we were not expecting, and I can't quite explain why this is happening. This is the same test with lasers from a different vendor. It has that same kind of issue, range and bearing dependent error. And here we actually ran one system twice, about 6 months apart, and found that the error changed on that laser over that period of time. So we have error that is different by model, error that is different by actual physical build, like unit A, unit B are the same model, but different incarnations, different physical assets. And then you also can have error that changes over time, unit A in January versus unit A in July. The other weird thing about unit A here is that you see these little hitches every 10 degrees or so, where the accuracy returns and then gets worse again. That also is not present on these other units. Just something wrong with this particular laser. Lens flare can cause issues with time-of-flight cameras and stereo cameras. Here we tried to induce lens flare by shining lights directly into a stereo camera, try to see what would happen in terms of corruption of data. And we see that there is some loss in density, sort of a isometric looking down view on this scene. And you see that where there are these very specular lens flare objects that you lose 3D data in those parts of the scene, but there's no incorrect returns being caused in other parts of the scene and no data sort of in the middle of the air or anything like that. I'm going to finish up with a series of tests that we're doing that are similar to optical. This is a 3D target that we've built that is modeled after the US Air Force 1951 target, and we're actually using it to separate measurement of range accuracy versus a 3D resolution. So range accuracy is how far away is an object and how accurate is that measurement, but there's also this sense of what is the smallest observable feature in a scene that a 3D sensor can locate, can measure. So this 1951 target is designed to do that in 2D space with black and white bars on printed paper. We have recreated that kind of target in 3D space with bars of different size that are different standoff from the background, and then can do the same kind of scoring in 3D. This is a process that we are still finishing. We haven't fully built this whole data pipeline, so the results here are a little bit more qualitative than quantitative, unfortunately, at this point, but there's still some interesting results. So we take this target, we put it in front of a 3D sensor, we capture some data, we then have a model of this target, and we use that model to identify and segment the model out, or the region of interest out of the 3D point cloud, which is being shown here. And then the outputs are colorized depth images and error images. Looking at stereo results first, on the right-hand side you see a range image. Blue and white colors here are the background of the board, and then pink is data that is being returned that is a higher elevation off that background. On the left, we have colorized the data with respect to error from the understood model of the board. So here, red means that the model is in front of the measurement, blue means that the model is behind the measurement. And you see on both of these images that we've overlaid sort of white and dark lines that show where we think the model should be And as I said, this is still in process. So you see in the top right corner that our alignment of the model to the board is a little bit off, and our white bars are actually in the blue instead of in the pink. So that is causing the model versus measure error image to be incorrect in the top right corner. But despite that, there's still some really interesting things here. You see first in the bottom left of the range image that the horizontal bars stick out much more cleanly and are much more accurate than the vertical bars. The vertical bars have a lot more smearing and incorrect returns between them. This is caused by two different things. One is that the stereo matching process works horizontally, so the edges of objects in the horizontal direction are less accurate than the edges of objects in the vertical direction. And the way that the stereo matching algorithm also works is it's propagating uncertainty along that horizontal match. So it's actually blending a little bit more in the horizontal direction than the vertical direction, which is what causes this sort of webbing between the vertical bars and not the horizontal bars. You see that on the right-hand side that the vertical bars are more observable than the horizontal bars. They disappear more quickly. And this is really interesting because with these large targets, you see the horizontal bars better. And then as the target gets smaller and smaller, that webbing actually helps you find the target. And you see on the left-hand side that even the very smallest target here is observable in the vertical direction, but not in the horizontal. This all makes sense once you start thinking about how these sensors actually work, but from first glance is a little bit confusing and strange. The one thing that we also did with this target that's a little bit different from the 1951 target is we put a vertical ramp in there. I'll flip back 2 slides. You see it on the bottom edge of the screen, this large ramp that's much taller than any other object in the scene. And you see that the stereo camera sees that fantastically. It's almost perfectly white. It's a really accurate return on that. In contrast, this industrial time of flight camera, immediately you see that it's much lower resolution. There's only 3 or 4 pixels on the large targets and much, much less data on the small targets. You also see that that ramp is basically invisible, that there's a little bit of data on the top half of it, but once you get halfway down the ramp, it immediately blends into the background. And this is, again, the tallest target on this object. That should be bright pink, like some of the bars are. But again, when you start thinking about how these sensors work, it makes sense that it's emitting IR light, it's hitting that ramp. The ramp is matte, but still some of the IR energy is being reflected down away from the camera instead of towards the camera. That is reducing the amount of signal that the time-of-flight camera has to see the ramp and making it more difficult to see that kind of geometry, and it's just blending in with the background as a result. You also see that there's no difference in horizontal versus vertical resolving power on these cameras. The horizontal and vertical bars are basically identical in terms of performance and accuracy, and there isn't the webbing that you see with the stereo cameras. And finally, a time-of-flight camera. Again, this is a more consumer-grade, lower-cost unit, which has very similar performance to the industrial camera. The one difference is that there's more sort of incorrect and errant returns along the edge of the target, sort of these hot pink pixels where everything should be blue along the outside. So in general, I have a few takeaways. That first, that there's no perfect sensor. They all have limitations. They all have edge cases. And our advice and what we do whenever we build systems is to think very critically about the performance and non-performance criteria that matter to the application at hand. And just because someone's using a particular sensor modality for one application and having success with it does not mean that when you put that same application in a different environment, or if you have a different application in that same environment, that you should be using that same kind of sensor. You really need to think critically about what you're doing with the data, how these sensors work, what the edge cases for these sensors are. Are you going to see those edge cases in the environment that you're operating? And really the only way to know that is to find data or to have experience with this, unfortunately. And there isn't generally much of this kind of data published or available. So our recommendation is ask the sensor manufacturer, if you're able to provide the sample data of the environment or the application that you're particularly interested in. You can obviously collect it yourself, or you can turn to people that have experience with this kind of integration and have used these systems in similar environments, and they can offer advice and help you select what makes sense for your application. And lastly, there's a few resources here. I've put all the videos that I've put on the slide deck on this page on our website, which is not linked to from anywhere else on the website, so you'll just have to type that in. But all the sample videos are there. And then there's more detail about some of these products on our support page and sort of examples of different operating modes and things like that. And of course, there is a wide variety of different kinds of people that make 3D sensors. I've listed just some of them here. The left-hand side are generally stereo and time-of-flight cameras, right-hand side LiDAR systems. But there's a whole host of available sensors on the market, which is great for integrators and people building systems. So I think that's about it. Happy to answer any questions that you have, and thank you.
Thank you, Chris. That was
absolutely
great. I really appreciated how you showed multiple videos of the same scene, so it was really clear to get a sense of what the difference is between the multiple sensors.
Yep.
Thank you. That was great.
Absolutely.
If anybody has a question, please line up behind the microphone in the center. And we have one question.
Hey. So a lot of data you present seems to be using a larger baselines on centimeters.
Mm-hmm.
What would be your considerations if you had to build a system with a super narrow baseline, like 10 to 15 millimeters? And how would it change some of the data you have here?
10 to 15 millimeters.
Yeah.
But that'll make mechanical rigidity a lot easier, which is great, because one advantage or disadvantage of wide baseline stereo is that to maintain rigidity between the two cameras gets trickier and trickier. I don't think there's any inherent challenges in making those sorts of systems, but obviously the calibration process becomes more and more critical as all of the dimensions of your system decrease in scale, and you're just going to be limited by fundamental limitations on accuracy based on the baseline. With stereo systems, as baseline gets wider, depth accuracy gets better. So it's just part of that triangulation problem. There are ways to combat that with higher resolution cameras, but then the computational process becomes more and more difficult. And you also require a scene that has enough texture to take advantage of that higher resolution. Super high resolution image of drywall is still pretty textureless.
Yeah. So in your test result of the stereo camera, you said the bleeding between the
vertical bars?
Yeah, vertical bars are caused by the optimization from the neighborhood, right?
Mm-hmm.
But if you do the optimization from multiple directions scanline, will it improve the?
That would help. This camera uses a 4-direction optimization. It's not an 8-direction system because that would increase the latency of the camera.
I see.
So that's part of what's causing this.
Yeah.
But it's also just the ambiguity on vertical edges versus horizontal edges because of the two different viewpoints.
Okay, thank you.
Hello, my name is Walter Bell. I'm curious about the distance towards the camera to the depth test board. Has this been on different distances tested or only on one?
Yeah, so the data here was all somewhere between 2 and 3 meters. I don't remember exactly how far away. And the board is about 1.25 meters square. That's obviously sort of pushing the limits of a time-of-flight camera from a detection perspective. So we've redesigned this to have larger features and to be able to test at greater distances.
Okay.
Yeah, we're actually...
Closer tests?
What was that?
Tests where you have been closer towards the board?
We absolutely can do that. I don't have data from that right now.
Okay.
Yeah. We're actually putting these in a dust chamber that we've built that's 60 feet long, and then going to be looking at resolving power of all these systems at different levels of ambient dust at different distances. You can't actually buy a chamber that is designed to suspend dust, so we had to design that ourselves. Which is its own pretty interesting challenge. Yeah.
Thank you.
Hi, Douglas. One of my questions is regarding, most of the images you showed were kind of a camera at a static point, and then the different types of cameras had, areas where they had trouble seeing, areas where they saw better. I was wondering which of these technologies kind of lends itself to if you're you're going to be moving around and tracking, and you're going to get different angles, different distances. Are some of them going to give you kind of the same data, or are some of them that extra data going to kind of allow you to correct more for the
Yeah.
deficiencies, and which would kind of work better under the condition that you could give it a bunch of different angles?
That's a great question. Yeah, so you're absolutely right that all this data was from static cameras. That's because it's easiest to analyze the accuracy with a static camera and a static scene. We build lots of mobile ground robots. Our robots move around in the world. So like, when we actually use our cameras in the systems, they're always moving around, and any 3D or 2D laser or time-of-flight camera has the same sort of use when we integrate them. In terms of general advantages or disadvantages of modalities as they move, I guess the two things you need to pay attention to are motion blur, and it's caused by two different things. With time-of-flight cameras, or three different things. With time-of-flight cameras, motion blur is caused by the multiple returns and sort of long integration time in that signal-to-noise extraction with all the different wavelengths, and they're aggregating data together over time to try to find signal from noise. So that can cause motion blur. With 3D lasers, you have the scan time that you have to compensate for. So you have to have very accurate understanding of system motion through the environment to back out, I'm moving at 90 degrees per second horizontally, and I'm taking a 20 millisecond scan, and that actually introduces a fair amount of angular shift over the course of those 20 milliseconds. And then with stereo cameras, motion blur is caused by visible blur. If you have long exposure times and you're moving around in the world, you're actually basically defocusing the image. And when you do that, you're reducing the visible texture that's available for the stereo matching algorithm to key off of. So that's something you definitely have to pay attention to with stereo cameras, is to keep the exposure time short so that when you are moving or when things are moving in the world, you're still able to see them sharply and therefore get good range measurements to them. A great sort of example of that is if you point one of our stereo cameras up at a drop ceiling and you start rotating it very quickly, the small texture of the drop panels disappears first, but you still have the big bars between the drop panels because those have enough visual texture that they hold up even with a fair amount of motion blur in the camera data. But that is something you have to watch out for. And definitely use a stereo system with a global shutter. Rolling shutters cause all sorts of other bad issues when you're moving. Yeah.
I know up front you said you didn't look at structured light versus stereo cameras, but maybe you could make a few comments about advantages and disadvantages of the two?
I guess in the environments that we operate in, indoors and outdoors, it has seemed to us that time-of-flight cameras are basically usurping the advantages of structured light from a cost and computational requirement perspective. So that's why we turn to those before structured light. That's not totally true. There are advantages to some of the costs in structured light systems. And if you have something like an assembly line with a conveyor belt, doing a very simple structured light system makes a lot of sense. You can get very, very accurate measurements on objects moving down a conveyor belt with a very simple structured light system. But those systems don't work as well, don't provide the same kind of horizontal and vertical field of view and range that these other systems provide, which is useful in mobile applications.
I'm looking for applications that work on a millimeter resolution. What concept would you follow first, and what would you pay attention on? Just the noise, or are there other things you have to look on?
That's tricky. I guess to offer any recommendation, I have to learn more about what you're actually looking at and the particularities of its surface and material and things like that. One advantage of stereo is that there's no fundamental minimum accuracy. With enough resolution, with a wide enough baseline, with good enough optics, you can build very, very accurate matching, but you need to have texture that allows that matching to occur. I guess maybe we can talk offline and I'll hear more about what you're thinking about.
Okay, let's do that.
Yep.
Do you have any tips and tricks for dealing with the craziness that you see in time-of-flight sensors? I mean, you mentioned, hardware-wise, you could have a diffraction, whatever, but software filters or any such thing?
I don't have any good answers for you there. there's only so much you can do to recover really big distortions in the data. Yeah, sorry.
Also, stay up for the next talk on
Yes.
time-of-flight sensors, which is...
Yeah, he may have some better answers
may
for
have.
you. Yeah, that's a very good point.
Actually, I have two more questions. One is the stereo matching. I assume you're using some semi-block matching or those kind of algorithms.
Yeah,
So
our
do you
cameras
see,
use semi-global block matching.
yeah, do you see the deep neural network-based stereo matching algorithm will improve the quality?
Absolutely. Yesterday I was in some talks where they showed results from that, and you can end up with much cleaner edges on objects and much more accurate data, but there's definitely a computational cost to that. Our cameras use an FPGA to accelerate the matching process, which generates about 15 million points in 6 watts-ish. If you were doing that on sort of general purpose processors, it would be at least an order of magnitude more power and many frames of latency. Mm-hmm. And that same kind of optimization effort needs to happen to move those CNN-based approaches into real-time hardware. So as far as I know, that hasn't happened yet, but is definitely an interesting area for sure.
Yeah. Another question is what's your opinion of the multi-view or array imaging? I mean, the cost and the improvement on the quality.
Sorry, the multi-what?
Multi-view array. I mean, I assume you're testing two-view stereo.
Oh, you're saying like 3 or 4, or adding more cameras?
Yeah.
Yeah, that helps a lot, especially with very repeating patterns and ambiguity. If you had chain link fences or things like that are very repeating. Again, you're adding a lot to the computational problem. So we don't have much experience with that because we generally build mobile robots that are power limited, they're battery powered. So there's only so much computational budget that we have. Yeah.
Okay, thank you.
We have time for one more question or two. I'll ask a question.
Okay.
So it's great that you showed us how you test the sensors. I think that's really very useful, a lot of good insights. But do you pay attention to tampering? Because some of these sensors can be tampered with. So do you test that?
In terms of like someone maliciously trying to...
Yeah.
In general, yes, but on our systems, we pay attention to that a lot. Sort of information assurance and making sure that someone's not putting malicious software on a robot or getting in there and changing parameters or sort of calibration or things like that. We lock that down very, very carefully in the systems that we build. In terms of the components that we build, I guess we haven't put anything into like preventing someone from opening it up and like changing the lens and then totally corrupting all the data. But if someone were to do that, you would totally corrupt all the data. You just wouldn't get any matches. I mean, if you take a calibrated camera and you replace the lenses with a different set of lenses.
But visually, you don't have a way to test the tamper.
Visually, no, and the camera wouldn't know that the lenses had been changed, but you would not have useful data out of the system, and the rest of the system would realize that. Our cameras, just like all other sensors, are sort of data providers, and there's only so much consistency checking you can do locally, and at some point it sort of falls onto the system to do that sort of checking between different overlapping sensors and making sure they agree with each other and things like that.
Well, thank you. Please, let's give another round of applause. Great talk.